Welcome back, everyone. So Anjan, I think, has made my job very easy for this lecture, and let's hope I can keep the momentum going. So the first couple of slides will show you in pictures some of the things that Anjan was discussing. Okay. So the first slide is, so this is an equation from yesterday. That's the Hubble constant as a function of the parameters, right? And A. And so then different of these terms dominate at different times, right? So Anjan made the point that at early times, this is the guy that's dominating, and so matter domination at early times, and then the constant is dominating at late times. And so we can make a plot of what is the scale factor as a function of time, right? So remember yesterday when Anjan wrote up on the board the expressions for the scale factor and the expression for time, and I said, oh, we could have actually written out what is A as a function of t, because I need it for this, and so here it is. So this morning Anjan derived A as a function of t. You know, A is t to the 2/3 in matter domination. A is t squared in radiation domination. So this is that, okay? And so this is A as a function of t for radiation, followed by matter domination, followed by cosmological constant, okay? Okay, so I'm going to take the same plot, and we'll just rotate it, okay? So that's the same guy. And so now this is t, and this is A. And this is the thing that Anjan was describing about the slope of this curve, okay? So remember he was saying, oh, you know, I can think of the thing that is proportional to t, that is like the Hubble horizon, okay? Whereas the thing that is proportional to A, that is like the scale that is just being stretched, okay? And so it is on these kinds of plots, so it's the same thing, right? So there's t and A, okay? So here's the A, here's the t, okay? And on this plot, you can ask, if you have a line that is proportional to A, that is the scale that's being stretched. And then he was describing, you know, what happens if a mode crosses into the horizon before it was outside the horizon, yeah? And so this was the t enter for a longer wave mode and a shorter wave mode, okay? And so that's why this axis is saying what's the wavelength of the mode. So this guy is short, this guy is long, okay? So this thing is, you know, a fairly steep function, so you know that all these curves are going to cross them. And so the motivation for something like inflation is the idea that, you know, if they were all outside the horizon at some time, then how is it that they all know about each other at the present time, right? And so the idea of inflation is trying to solve that problem by saying, in fact, this boundary doesn't keep dropping like this. There was a period when it was quite flat, okay? And that way all the modes were inside the horizon, then they came out of the horizon, they re-entered. This is not a course about inflation, so we won't get into this. We're just talking about this region here. And then Anjan described what happens if a mode enters during radiation domination or during matter domination. Yeah? And so if a mode enters during radiation domination, then it doesn't grow, or it grows as the log with time, right? Maybe it oscillates. Whereas if it enters in radiation domination, then it grows proportional to the growth factor, okay? And so meaning if a density fluctuation of that wavelength will grow with a growth rate proportional to A.
In matter domination.
In matter domination, if it enters in matter domination, right? If it enters earlier, then no.
The slope of both are same.
Oh, okay, so sorry. So right now the slope of both are just showing you when they enter. But now we have to imagine what do they grow. So the next plot is going to try to show you. He derived this, so I won't go through this. Yeah? So this was just deriving the different growth rates. So you have it all written out here. And so, okay. So the long and short modes, after they've entered the horizon, they will grow depending on when they entered the horizon. And so this one is showing you, so this is matter radiation equality. If I have a mode that entered, okay, then it won't grow until universe becomes matter dominated, and then it will start growing. Okay? The other perturbation that was outside the horizon for longer and only entered after equality, so when it enters in matter domination, it grows. Okay? So that means that if outside the horizon, we have to ask now, what happened to these modes? Okay? Outside the horizon, these modes, whatever they were doing outside the horizon, this one will continue doing it until it enters the horizon, whereas this guy, if it was growing, will stop growing for this period of time, and then it will keep growing. It will start growing again once it becomes matter dominated. Okay?
What's L on the y-axis?
It's a length scale, what I was calling lambda before, so that's all. Okay. Okay. So here's the Newtonian sketch of what the modes are doing outside the horizon. Okay. So this can be done properly by working, carefully choosing a gauge and doing the calculation. I'm not doing that here. Okay. I'm doing the very simple argument here. The simple argument is like this. So first you start out with the Friedman equation. And in fact, when Anjan wrote things yesterday, the first time he wrote it without the curvature term. Okay? So it was very good it happened like that, because we'll start with such a model. Okay? One with no curvature. Now we'll imagine another model that has the same Hubble constant, but is slightly more dense. And if it's slightly more dense, then it's like a closed universe. And if it's a closed universe, it has some curvature. And so we put the curvature term. And so these are two very slightly different models. So I can ask, what's the difference in their density? And so the difference in their density will be, the model 1 minus the original model. So call this one model 1, right? So there's density 1. Okay? So we'll take this density minus this density, and we'll write as a fraction. Okay, so this is like a delta rho over rho. Okay. So if we just do the subtraction, right? So we will have this guy, and we will be subtracting these two guys. Okay, and remember we have h the same, so now there's just some algebra to work everything out, and all that survives is this k a squared term. Okay, and so now we can ask. So this is the delta, it's the difference of the two densities. It's a delta, so it grows as A if it's matter dominated, and it grows as A squared if it's radiation dominated. And so that means that outside the horizon, so while it's still radiation dominated, these modes are growing as A squared. Then they will enter the horizon. If we take the blue one, it's growing as A squared. Now it will grow as A in matter domination. Okay? This guy was growing as A squared. Then it doesn't grow at all. Then it will grow as A. And so that means that suppose this one had some amplitude that was twice this one. So in fact, suppose they had the same amplitude. Okay? Then simply because this one grew for a longer time outside the horizon, whereas this one entered and did not grow for some time, this one will now have a larger amplitude. Okay? And so this has an important consequence.
Technically, these two are different. Right? This is, you're talking about a growth of perturbation. There you are considering two hypothetical universes with the change in density.
Yes, and I was calling the difference a delta.
Yes.
That's right.
So you're assuming that a portion which is a perturbation will evolve as a separate universe in some.
Yes, that's right. That's the Newtonian kind of thing. That's a slight cheat. This can be done properly.
Yeah.
So it's just, yeah. Okay. So this is a messy plot. So that's why I tried to say many things before I showed the plot. Okay. So now this one is trying to show you what happens to different modes. Okay. So here is a mode, and this is trying to show you how it grows. Okay. Before we were just watching the lengths. Okay. So now we're actually watching the growth, and so the growth will be like a squared. Okay. But then if it enters the horizon, it will not grow, it might oscillate, okay? And then this is the time of decoupling. So this is the matter radiation equality. And so at equality, then it will start growing because now it's matter dominated, okay? And so it should start growing as a squared. So if I was drawing this carefully, this one is trying, once it is matter dominated, it should grow as A, okay? And so this slope is growing as A. So I should have drawn this one as growing as A like this, okay? But I didn't draw it like that. So we'll come back to that, okay? Instead, I drew it as it bumps up high, and then it asymptotes to that correct slope. So we'll come back to that. This is showing you the change from 2 to 1, okay? So what is happening here is that when you have a mode that enters and it doesn't grow, and now it's matter dominated and it can start growing, okay? There could have been, let's imagine that I had a dark matter mode and a baryon mode, okay? So the baryons are certainly the ones that are doing the oscillating. The dark matter will grow like as the log, something like that, will grow very little, okay? But will grow a little bit more than the baryons, okay? As a result of which, the two baryons and dark matter will also have different values, okay? Even if they crossed at the same time. They will have started with similar amplitudes because we said we start with adiabatic fluctuations, and so all components start with similar, if one is positive, the other is positive, that kind of thing. And so what happens is that the dark matter, it can grow a little bit more than the baryons can grow. And so later, when the baryons can start growing, they catch up with the dark matter until they grow with the dark matter. So there's a period of time when the baryons and the dark matter are doing different things. And this period of time is around the time of the CMB, of the decoupling, when the baryons are being pushed around by the photons and the dark matter is not. Yeah? Okay, so this has an important consequence, because if the baryons had oscillated and they had to grow without the dark matter to fall towards, to give them some enhanced growth, then the baryons would reach some amplitude today that is less than because there's also dark matter. So suppose the universe was omega matter 0.3, but all of it baryons. If it was all baryons, then all the baryons would do this, and then after decoupling, they would start to grow like this. So there would not be time to grow structures that we see today, because they will have not grown for long enough, and then they have nothing to give them accelerated growth, and so we will have less structure formation than we see today. So this is a very tough argument for models that want to say that all the matter can be baryonic. If all the matter was baryonic and you want to reconcile with observations of the CMB, you have somehow to explain how the baryons grew from that time in 1,000 expansion factors to the current amplitude. Yeah? And so that's a tough problem for some modifications to GR to solve, or for some models that are trying to play games with what is the, do you really need dark matter?
Yeah. Perhaps I'm kind of going ahead, but can the same argument be used to set some limits on on dark matter self-interactions?
Yes. So one of the things that I'll be doing later is not for this. So I was going to do like what happens with the BAO, but similar arguments with what happens with the BAO apply to the self-interacting dark matter. And so people have looked at some aspects of this. Yeah. Okay. So what does this mean? This difference in growth. Okay. So if you have two modes, okay, so 1 and 2, so two wavelengths, okay, and they will enter at different times. Okay. So one entered at A1, the other entered at A2. Okay. And suppose they both entered during radiation domination. So then what will happen? Because they entered during radiation domination, one was growing as A squared, while the other had stopped growing because it entered. And so that means that their amplitudes will now differ by a factor that says, the one grew for this much longer for the ratio of these two expansion factors. Yeah, because it grew for that much longer, while the other stayed constant. But this ratio is basically their wavelengths. And so we're writing now their wavelengths, instead of lambda 1, 2, we're writing K1, K2, the K mode 1 over the wavelength. Okay? And so that means that we're expecting the K modes that are short, so I shouldn't say K modes that are short, the wavelengths that are short, that entered earlier, we are expecting them to have suppressed power because they didn't grow. And that suppression will be, the A squared suppression will translate as a K squared, as a wavelength squared. Okay? And so that means that the modes, for all Ks that are wavelength shorter, so K bigger than K equality, they will all be suppressed. If you are twice K equality, you are suppressed by 2 squared. Okay? And so that means that you can think of whatever the distribution of K mode strengths that you had. It could be that all K modes have equal strength, for example. We'll argue in a second that's not the case, but suppose they all had equal strength. Then, as a result of this process, they will no longer have equal strength because the short waves, the big K, are suppressed by K squared. So this is that suppression. 1 plus K over K equality squared. If K is big, if K is very big compared to this guy, this is the 1 over K squared that I was talking about. If K is less than K squared, there's no suppression.
So that's why you see a downward slope in the power spectrum.
So this is why you see a downward slope in the power spectrum. Okay? And so we think that the power spectrum started out as proportional to K. Okay? And what happens is that we haven't, unfortunately, we haven't set up the formalism for what does power spectrum mean, what does correlation function mean. So I will set that up, but for some of you, I think you already know. Yeah? So I'll set that up, and it's in the notes that you have. Yeah? But the way to think of it is this P of K is 2 powers of the delta. So let me write here. This is a delta with a delta. It's something like this. So there's 2 powers. And that means each delta mode is getting suppressed by this term. And so there are 2 of them, and so there are 2 of those terms. Okay? And so what is happening is that you're getting a suppression. So this means this has slope k at small k. And then there will be a suppression to k to the 4. So 1 over k to the 4. So k divided by k to the 4 at big K. So k to the minus 3 at big K. And so we're expecting a slope like this, just because of this effect, because modes enter at different times. Okay? All right? And so don't worry about the Fourier transform. We'll do that later. And so this is that diagram, okay? The mode started out like this, and then they have a suppression of power. This is the 1 over k to the k cubed. Okay. So in Anjan's discussion, he mentioned the scale associated with a mode that enters before equality. Okay. And the number that he was using was some number that's 10 or 15 megaparsecs, no, to illustrate the argument. So here we can ask, what really is that scale? So let's take some rough numbers. Suppose we take the time of the CMB. So the time of the CMB, the time is age 400,000 years. The time now is 14 billion years. So I can take the ratio of those times, okay? And I was doing it earlier. That number is like 35,000. Okay, so it's 35,000 is that ratio. That's the ratio of the times. But I should compare that with the ratio of the expansion factors, because in the expansion factor is factor of 1,000. Yeah. And so factor of 35,000, factor of 1,000. That's a factor of 35, okay? And if I take the distance to the last scattering surface, so that's the Hubble scale today, so if I take that scale, there's a factor of 35 difference between that scale and there's a difference of 35 between the Hubble volume at decoupling and the Hubble volume now, okay? And so the distance to decoupling is 14,000 megaparsecs, so that's the wavelength, okay? If I take the 14,000 divide by 35, you get of order 300 megaparsecs. So that's this scale, that's the K equality, okay? So it's not the 15 megaparsecs or so, it's more like a few hundred megaparsecs, okay? And that's the peak in this power spectrum. And so it's pretty simple arguments that are leading to this scale. It's the scale of matter radiation equality, and the cut 1 over k cubed is coming from modes entering at different times. So this is a generic prediction. And so it's interesting to ask, do we see anything like this in data? And so here are crude measurements of the power spectrum of fluctuations from data, from the different probes of data that we discussed very briefly last time. No? So clustering of galaxies, clustering of clusters, weak lensing signal, all of these, they only probe, each one probes a limited range. No? The lensing probes some small scales, not very big scales. Clustering of galaxies probes slightly bigger scales, longer wavelengths. And if you leave the amplitude free, so you can make them all line up with each other, then you get this shape. Okay, so you get kind of the right shape. You say, why am I doing this? I'm not allowed to just take the amplitude free as I want, okay? And so one of the things we'll be doing in the next few days is working out why this is a reasonable thing to do. Okay? And so we will work out models where a linear multiplicative factor to the power is an okay thing to do. It's not great, but it's an okay thing to do, all right? And we'll motivate why and the limitations of doing that. But there was some excitement that you even get the right shape from such a simple argument. Okay, potential wrinkles. So so far, this is true for the dark matter. But remember, the baryons, they're oscillating differently for a while. Okay? And so there is a transfer function. This thing is called a transfer function. For cold dark matter, there is a transfer function for baryons. There is a transfer function if there were neutrinos. They will have their own transfer function. Okay? So depending on what you think the constituents are of the universe, each of those species will have its own transfer function. And so I've drawn one transfer function, which is the one that people use sometimes when they're modeling neutrinos. Okay? You notice that this is a 1 over k to the minus 5. So there's a serious extra suppression at high k for the neutrinos, for the warm dark matter. We'll talk about neutrino models later. So this is just to show you that they show up in the power spectrum in this way. They cut at high k. For the baryons, so how do you treat the power spectrum? You take the power spectrum. The power spectrum is, now you take the fraction of matter that is cold dark matter plus the fraction of matter that is baryons plus the fraction that is neutrinos and so on. You just sum up the transfer functions weighted by the relative fractions in each. Okay? So it's as simple as that. It's slightly simpler than that because we think omega baryon is 1/6 or so of cold dark matter. And if I take 1/6 squared, then that's an even smaller number. So you can almost throw the squared term away. And you can just take this guy squared, which we saw before, and then twice this times that. Okay? So you can think of the power spectrum as just the sum of two terms. The one that we said already, that is cutting as 1 over k cubed, and one that will be this kind of cutting, but with the one for the baryons. So I've written here the one for the baryons, a very crude approximation for the one for the baryons, and we'll derive this soon. Okay? Yeah.
The transfer function of baryons, I mean, there has to be some omega CDM factor hiding inside that, right? Because it will also be influenced by the...
So what will happen when you multiply the two? You're going to, for the effect on the power spectrum, you'll get the product of the two. So you'll get this times this.
No, what I'm saying...
You mean sitting inside here itself? So you think inside TB itself there should be...
One is TB essentially tells the how accelerated growth it is. It will also be affected by it.
So what will happen, there will be some effect sitting inside this parameter that has that, okay? And this is a slightly simplified version. To get ahead of the game slightly, this one would be if the baryons were, it's almost like if the surface of last scattering were very narrow. We know that it's actually some thickness, and because there's some thickness, I should multiply this by something like a Gaussian. Okay? But we will come back to this. The basic point of this slide for now is just to say you'll get the sum of two terms, and this term is a term that has oscillations because the baryons were oscillating. Okay? In K-space, it seems more complicated than it is. You'll see in a second when we do the real space picture that why this is so natural, why oscillations are so natural. Okay? But we're going to see that you're going to get a term which is the smooth kind of guy that we saw before, plus a term that has oscillations. And so if you looked carefully, this one actually has some slight oscillations. Okay, and those oscillations are small because the baryon to total fraction is small. Okay, so you're just adding on top this small term. Okay. Okay. If there were more baryons, so this incorporates some of the effect you were mentioning, right? So suppose we keep a lambda CDM model, and now we start tuning. Always the matter is this, but first there were very few baryons, and now we're increasing the baryon fraction. So as you increase the baryon fraction, then two things will happen. One, you will see the oscillations more obviously because of the baryons. Okay, so you can see the oscillations more obviously here than up there. And the second is this extra suppression, because if you don't have the dark matter to pull you up, then you are more suppressed. Yeah, and so this is the effect of adding in ever more baryons. And if you put in too many baryons, then you will be down here, and that's the statement that you wouldn't have made small-scale structures by the present time, and that's why we need some of the matter to be dark matter, non-baryonic matter. Okay. All right. So these are this was the picture in K space, where short waves are here, long waves are here. This is the Fourier transform of that thing, okay, to show fluctuations now on physical scales, small scales, and big scales. Similarly, there's a shape, and we can put the different data sets and see if more or less they trace that shape. Okay. This is just showing you, we could have done the analysis in real space or in Fourier space, and you get, from the data, you get a consistent story.
This is sigma square or sigma?
This is sigma squared, yeah. But it's, again, we'll define all these things, we'll define these things soon. Okay. Okay, so I just wanted to show you that, where the CDM power spectrum comes from. So now I want to switch gears a little, and I want to talk about the connection between, if I imagine, let's take a very special case. Let's say that there is a matter concentration exactly in between you and me, and so the light has to travel. It cannot travel straight to you because it would hit the lens. It would hit the mass concentration. The light that would have gone up and you would not have seen, now because of the mass concentration, it reaches you. But suppose this is spherically symmetric. Then a photon can come like this. A photon that would not have reached you will now reach you. A photon that would not have reached you will now reach you. So you will see many photons coming from me that you would not have seen otherwise. So it was lensing, it was magnification, because you got more photons than you would otherwise. You will see a strange image of me, because you will see photons coming from this direction, from this direction, from this direction, because you think photons travel in a straight line. You will see an image of me over there, over there, over there, over there, over there. So you will see an image of me in a ring like this. Because of gravity. If gravity, so if the lens, if the mass is bigger in the middle, the bending will be much stronger.
Sir, how is this sort of different from the ISW effect that you talked about?
The ISW effect was, as the photon travels, it can pass by the lens, it will change its energy. But we didn't describe the fact that it will actually change its direction of motion. Yeah? So that's the only difference. So the ISW effect was paying attention to the energy, whereas the gravitational lensing effect is paying attention to the direction from which the photons arrive, the deflection angle rather than the energy change. Both have to do with the mass along the way, along the path. Okay. We'll do those things more also. Yeah. Okay. So what we're going to try to do now is we'll try to put together the physics that set the shape of the power spectrum, cold dark matter plus baryons, with the physics that made the CMB. Okay? And so to do that, I need to add one more ingredient. And that one ingredient is when gravity starts to make structures form. So we heard linear theory, what is the growth? But we don't have a sense for really what it means. Like, because of gravity, did a particle move 1 megaparsec, 100 megaparsecs? How far did a particle move? So we'll make an estimate of that, but first here's a simulation just to motivate. So this is a simulation that shows a distribution of particles. This is 120 megaparsecs, so this is like 350, something like that, megaparsecs, at redshift 20. And the universe is quite smooth. It's already a little bit lumpy. You can see there are some slight, underdensities. White is overdensity. Now we'll run the simulation forward. That's the present. Let's go back, forward. So if you look in the middle, the thing that is big at the present time in the middle was always there, even in the beginning. Yeah? If you pay attention to this hole here, that hole gets bigger, gets bigger, gets bigger. The underdensities, the matter is going away from the underdense regions and is going to fill the overdense regions. Capitalism, no? And so the important point is that nothing came from this side of the box to here. Nothing came from here to here. Nothing came from here to here. This stuff, it got all its mass from basically the region around it. Basically off order 10, 20 megaparsecs, not 100 megaparsecs.
What sets the scale for it?
We're getting there, okay? But so the key idea is nothing moved. Nothing moved very far, okay? And that is the most important assumption or statement for everything that I'm going to say from now on, for the rest of my life. Okay, certainly for the rest of the course. Okay, so nothing moved far. Okay, so that piece there, it looked like the universe was quite inhomogeneous, right? Because there's a big lump here, there's a big lump here. Okay, and we haven't yet said where galaxies are, but you can kind of guess they're going to be where the stuff is yellow, and we will motivate why soon. Okay. But let's look on very large scale. So this is now, that was 350 megaparsecs. This is 3 gigaparsecs. And so you can see basically the structure is pretty homogeneous. It's lumpy here, but on very large scales, it's one place is like another place. Okay. All right. So what is setting the scale? So this is still not physics. This is still an observationally motivated estimate. Okay? You look in the sky and you say, oh, how fast are things moving when I look at them? And the things that we see, they are moving a few hundred kilometers per second. Perhaps the thing that we have the best measure of is our own motion with respect to the CMB. You remember the CMB is 2.7 degrees Kelvin. But if we are moving, then we will see a Doppler shift in the direction of our motion. So we can measure how much colder it is behind us compared to in front of us. And so we can measure the speed. That speed is 600 kilometers per second. Okay? So we can take as a rough estimate of speed, we'll take here 1,000 kilometers per second, just to get a scale. Okay? So if you are moving 1,000 kilometers per second for 10 billion years, roughly the age of the universe, then you will move 10 megaparsecs. Okay, so that's why I've chosen these numbers. These are easy to remember. And now, I can make this 200, or I can make this 20. But more or less, that's the scale. Importantly, it was not 100 megaparsecs. Okay? So just empirically, we know that the scale is small, if we are nowhere special, and the galaxies that we see are nowhere special. Okay, so that means we don't expect anything to move very far. And that's why we call this the cold dark matter model. If it was, so the cold is referring to speed small compared to speed of light. Neutrinos would be warm dark matter because their speeds are relativistic. So they are fast, not fast compared to the speed of light, but close to the speed of light, yeah.
So this cold is, we know it from observations or it's an assumption?
Okay, so we know from observations that we are moving at these speeds, and the other galaxies that are nearby enough that we can estimate speeds for, they're all of this order. And so observationally, we know this is true. So the theory models, the lambda CDM models, they have put in the fact that it's cold. And you will see, tomorrow we'll discuss a little bit how people set up initial conditions for simulations to model these things, to see exactly how they put in that the speeds are small, so that it's cold. Yeah?
When we say cold dark matter, I mean, strictly speaking, it is just not non-relativistic, right?
Yeah, strictly speaking, it's just not, that's correct, yeah, that's right. And so, yeah, so here my cold is really just saying you don't travel far. Yeah. Okay. Dark, because we don't know where the galaxies are. Gravity was the only thing in the simulations, okay? And matter. Gravity was the only thing that mattered, okay? Okay, so because of this, the field at late times contains a memory of the initial conditions, right? Because structures that are 2 megaparsecs in size, they can be different from the initial conditions. But structures that are 20 megaparsecs in size, maybe there were small rearrangements inside them, but if it was a 20 megaparsec giant, it's still a giant. Yeah? And so that is a vital part of how we do cosmology today, okay? That the late time field remembers the early time field. And it didn't have to be that way. And so as I'm going through all the rest of the lectures, you should have in the back of your head, if there are neutrinos that are moving fast, that will move much more than 10 megaparsecs, then none of what I say will be true, okay? I'm overstating. A lot of what I say will still be true, but there will be serious modifications if there are neutrinos and they're a substantial fraction of the dark matter because of this. Okay. All right. And so the question is, can we use this fact that nothing moved more than 10, 20 megaparsecs since a redshift of 1,000? Yeah.
Give the velocity with respect to the other galaxies. How do you know others are stationary and the other ones which are moving? Could be everything is moving somewhere else.
Oh, it could be all of us are moving together. One giant bulk flow. That's possible, yeah? But so then it's the usual thing that an overall gradient is not something, translation invariance means we don't care about that. One bulk flow, yeah? So if the whole universe is moving with speed of light somewhere, we don't care. We can only make difference measurements. Yeah? But we do care if our piece of the universe is moving this way compared to the CMB, and some other piece is moving, it's still in our Hubble volume. We would care if that was happening. We don't see evidence for that. Let me give you a crude way, okay, because we haven't done redshift space distortion, so we haven't yet made good estimates of velocities, but I'll give you a crude estimate. And the crude estimate is, remember we made the Hubble diagram? And when we made the Hubble diagram, it was kind of a linear law with the speed as a function of distance, okay? And there's some scatter about this line. And so if all the particles were moving, so in Anjan he wrote out an expression where he had a velocity that he called u, and he said that, he started out and he said r is some a times x. Then he took a derivative of r. That one was u. This one was h times, he wrote it as this, so hr plus an a dx dt. Okay? So this is the Hubble law. These are the speeds. Okay? And so if everything was Hubble law, they would be sitting on this line. And we talked about whether the line actually does like this or does like this. Yeah? But everyone would just be sitting on the line. So the scatter from the line, if it is real, if it's not a measurement problem, that's because of these speeds. So we can measure speeds like that. Yeah? It turns out that around here it's easy to make those measurements. Further out, it's a lot harder to make the measurements. Further out, we have to do it with redshift space distortions that we'll describe. But so we know for a fair number of 1,000 galaxies close to us, we know these speeds are small. So it's not just 1 or 2 galaxies. Yeah? And then from redshift space distortions, we actually know that that the estimate that I get, that we are not unusual, that it's a good estimate. Okay. So we're trying to use the fact, or we're asking if there's any memory. So we have said there is memory of the initial distribution in today's distribution. Now we want to know if there is if that memory is useful. Okay. So we start out and we say CMB was interaction between the photons and the baryons. Okay. And so the question we want to know is whether structure today remembers this. Okay. So here is an illustration, an idealized illustration. We'll make it more realistic soon. The idealized illustration is you start out with a spike. So this is a place in the universe where there happen to be more stuff. Adiabatic initial conditions, which means more photons, more baryons, more dark matter, more neutrinos. Okay? What happens? Photons, they're going at the speed of light. Well, they want to go at the speed of light, but they hit the baryons. And so they don't go at the speed of light, they go at the sound speed. They push the baryons. So it's trying to show you that the photons push the baryons, so the baryons come out from here and they go out over there in a shell. Okay? Yeah. The spike represents somewhere in the universe there happen to be more overdensity of everything because of adiabatic initial conditions. So if there's overdensity of one, there's overdensity of everything. Yeah? And it's asking if there was such a place, what happened? And so what will happen is such a place means if I have lots of photons, it means it's hot. So the photons are going to go to where it's cool. Yeah? So the photons are going. They're going to take the baryons with them because they're interacting with the baryons. And so they push the baryons. So they push the baryons until, well, universe is expanding. And so eventually it cools. Eventually the electrons get bound to the protons. So the photons can no longer push the electrons. So when they stop pushing, then the baryons stop and the photons keep going. Okay, so it's the photons. Photons should go at the speed of light, but when they push the baryons, it means that they actually bounce on all the baryons. Like in the movie that we did, we had the photons that do this before they go in a straight line. So they're doing this. That is making the baryons move. And then when the universe is cool enough, then they go in the straight line, and now they go at the speed of light. The baryons stop going. When they were pushing the baryons, then we say the baryons will move with the sound speed, and that is the roughly CS squared is 1/3.
That is the speed
That is the speed of the baryons. Yeah? So that is the speed with which the shell is moving from the center.
Speed of the baryons or speed of the oscillation moving? Sound speed, you mean the sound that moves, like the phase that propagates?
I mean, this is the wave that propagates. This is the thing that is going out. No? So this thing goes out with that speed.
Oh,
Yeah?
okay.
This is the combined baryon-photon fluid.
This is the combined baryon-photon fluid. Yeah? They have not yet decoupled, and so that the baryons are being pushed. And so you're used to, so we call it oscillation, but in this language it's a simple thing, right? You had a bunch of stuff here and they got pushed out because the photons are moving. Yeah? In many ways, this is the real space picture. In many ways, it's a much simpler picture of what goes on. Okay?
And
So,
you want that spike because you want a very higher density, no?
yeah, this is just to illustrate. Very soon, very soon we're going to say there could be a spike here, there could be a spike in many different places. But we'll look at one spike, then we'll do the superposition of many.
Because in initial stage, density would be very high.
Okay, the density is 10 to the minus 5, no?
Yeah.
Up or down. So actually the fluctuations are not very big. And so let's ask, what is this scale? Okay, so I have a crude estimate here. There's a slightly more careful estimate up here that does the sound speed for the baryon fraction and baryon to photon ratio and all that stuff. Okay, but basically, we know that it was roughly 300,000 years. Okay, so roughly 300,000 light years, factor of square root of 3. Okay, so 300,000 light years. 300,000 light years, there's factor of 3 to go from light year to parsecs. And so this is 100,000 parsecs, means 100 kiloparsecs. This is 100 kiloparsecs was the physical size at the time of the CMB, which was redshift 1000. So 100 kiloparsecs now has expanded by a factor of 1000, 100 megaparsecs. And so that means that we are expecting something in the baryon distribution on the scale of 100 megaparsecs. Yeah? From CMB physics. Okay? The fact that the CMB photons were released is telling us there must be something in the baryons on having to do with the scale of 100 megaparsecs today. Okay? This is a...
The initial profile of the spike is taken when the scale enters the horizon.
So this initial profile is taken at just some very early time. Remember, entering the horizon, here it really is it's a real space spike. No? So it's a position in space, and then stuff is going out from it. So we're not thinking of K modes anymore. Yeah? We're not thinking of wavelengths that have to enter a horizon. It's literally where was stuff moving to. And in this case, all the motions are slower than the speed of light, no? And the baryons are going slower than the speed of light, so they're always within the horizon, if you want to say it that way. Yeah.
So after the photons are decoupled, why don't the baryons just keep moving outside or collapse back?
Okay, so in reality, what has happened is that there is dark matter in the center, okay? And there's much more dark matter than baryonic matter. And the dark matter, by assumption, by prejudice, is weakly interacting, so does not interact with the photons. And so that spike is still there. And so this thing is trying to illustrate that. It's a slightly confusing plot. So don't look at all the 4 panels immediately. Okay? Let's just look at the first one. The first one is soon after the initial delta function. So you should imagine there was a first time step. You see, this is saying redshift of 7,000. So imagine redshift of 10,000. Everyone is sitting close together. Okay? Now, we have a spike in dark matter, spike in gas, photons, they're tightly coupled, and the neutrinos that are not coupled, they're going at basically the speed of light, so they're going out. Okay? The thing that is confusing about the plot is the heights. Okay? There should be much more dark matter than the other stuff. Okay, so these have been normalized so that they all fit on the same scale. Right? So that's the main confusing thing. Other than that, it's okay. So what you're really looking for is to see the heights of the peaks, to see where most of the baryons and photons are, the neutrinos as time goes on. And what you can see is the baryons and photons go out, the neutrinos go out further, the dark matter goes out a little bit because it feels the dark matter, it feels the baryons going away. But it doesn't go out that far, the spike in the middle is staying there. Okay? Then at redshift of 1000, now the baryons are not pushed by the photons anymore. So neutrinos are gone, photons are beginning to go away. The baryons are now responding to this because they're not pushed anymore by the photons. And so they're going to come back towards the dark matter spike. Okay? And so now you can see that the baryons are starting to come back a little bit towards the dark matter. Okay? Photons are gone, neutrinos are gone. And the dark matter spike is here, and now this spike will start growing with the linear theory growth factor. Maybe it will become nonlinear growth and stuff like that. But the idea is that there will be this spike of baryons on the scale of roughly 100 megaparsecs. Yeah.
Originally, why is it that photon is winning over the dark matter and carrying away? Because everything is hot and they are so tightly coupled. It's really because they're so tightly coupled. Baryons are more coupled with photons than they are with the dark matter.
Yes, with dark matter it's only gravity. No, because by prejudice the dark matter is not interacting with anything except gravity, right?
What I'm asking is that why is it that gravity of dark matter is not winning over the radiation vision?
Gravity is weak.
Yeah, it's essentially that. Remember, the fluctuations are 10 to the minus 5, no? So they're really small fluctuations.
Oh, has it also to do with the fact that the number density of photons is very large?
Number density is, photons is very large then. Yeah, you're close to, that's right. Early on, yes, that's right. That's right. Very good, thanks. Yeah. So anyway, so this is the sketch, yeah? And so importantly, we're expecting a little spike of baryons around every spike in dark matter, even today. Yeah? And so we have this feeling that galaxies are going to form where the baryons are. So galaxies will form here, and galaxies will form with these baryons also. And so what this is saying is, if I sit on a galaxy in the center, then 100 megaparsecs away, I should find a galaxy. That's the idea. Okay?
There should be something with much lower dark matter than this galaxy.
Okay, so in the time since then to now, it is true that the dark matter will also
rise up.
will come in.
Basically, the baryons will track the dark matter curve.
Exactly. That's right. Yeah. And so they will the dark matter. Just like when we were doing the power spectrum, we said the baryons oscillate and then they will catch up to where the dark matter is. So what that means is that as time goes on, this is redshift of 500. By redshift of 0, the blue is sitting here, and this has dropped down a little bit, and the black is sitting here. Okay, because then they are tightly coupled because of gravity. Yeah?
Can I move to the previous slide?
Sure.
Previous slide. Yes, the spike tells about hot dense matter. So hot dense matter radiates its energy. So my simple question is, when matter radiates energy, there must be some kind of interaction with field. So is there any field exist at the early stage of the universe that forces him to radiate energy?
I'm not sure what you mean by with some field.
Matter radiates only when it interacts with some kind of field.
So here you have the...
Is there any kind of field exist in the early stage of universe which force him, the dense matter, to radiate the energy to the space?
Well, so at very early universe there was stuff like that going on, but we're talking about much later than that. And so right now there's really just, if you want, there's the dark matter field, but that doesn't make photons, so it's not radiating energy away. Then there's the baryons and the photons. So that's all.
This kind of assumption that we understood that there exists some kind of dense matter and then it radiates its energy. Because suppose when we are going to study of the atomic physics, there is a laser system. When we push the atom from ground state to higher excited state, and then it radiates because there is an interaction with some kind of field which is called as electromagnetic field or 0-point electromagnetic field, something like that.
Right.
Is there any kind of field
responsible
to radiate him?
No, in that case, no.
They are always.
Yeah.
Baryons are there, photons are there, so and they will always interact.
And also you have to remember it's so hot that the electrons are not there with there's no atomic physics, right? Because
So I just so in the lecture you said that some baryons will catch up with the dark matter peak, and dark matter would catch up with the baryon peak also. So how much from these simulations, how much of the dark matter to baryonic matter ratio, how much of variation can I expect between galaxies?
Okay. So look at if you look. So the question is, how different is the baryon to dark matter ratio today from one galaxy to another? Okay. So if you look at this scale, so we've been saying this spike should be 100 megaparsecs. A galaxy is less than 1 megaparsec. Okay. So the variations can be quite big.
It can be quite big.
It can be quite big. There are a couple of you here who are working on clusters, and clusters we believe are big enough. Clusters, basically they assemble their mass from a patch that was 10 megaparsecs in size. So 10 megaparsecs, because nothing moves more than 10 megaparsecs, that's where you have the universal fraction. Smaller scales, you can have variation one place from another. But once you're big enough, a cluster assembled its mass from 5 to 10 megaparsecs. So we think there, the baryon to dark matter mass fraction is the same from one cluster to another, but not for galaxies. So galaxies are too small. But we're talking about much bigger scales here for now. Yeah? So we're not going to be asking what is the dark matter to baryon fraction in this galaxy and compare it to one over here. We're not going to do that. Yeah? We're simply going to say, if I'm sitting on a galaxy, do I see another galaxy 100 megaparsecs away? Yeah? This is the better picture, right? In reality, there was not just the one delta function. There's a whole collection of these things. Okay? All right. So with this, you certainly can't see by eye anymore a shell. But it is still true that if I sit on a peak here and I look 100 megaparsecs away, there should be a slight excess of baryons in a shell around this peak, around this peak, around this peak. Around every single peak, there should be a slight excess. Okay? And so we can look for this slight excess. And so that's the idea. This is the slight excess that is caused by the same physics that made the CMB. And now it's left over in the galaxy distribution. Okay. And so this is a cartoon of the effect, right? So the cartoon says, I should get, anywhere I have a bunch of galaxies, I should look 100 megaparsecs away, and there should be others. There will be, other galaxies in the middle also, but certainly at 100 megaparsecs there should be. Okay, so that's the cartoon. This is much more exaggerated than the real world. We don't look in the sky and see circles in the sky, or people would be jumping up and down, right? But we can do the statistical thing, right? We can try to look for this signal. Okay? There's one other respect in which this cartoon is a little bit unrealistic. So this is circles of 100 megaparsecs. But now some of the galaxies can be close to you, and some of the galaxies can be far from you. So that same 100 megaparsecs, if it's close to you, is a big angle. And if it's far, you see as a small angle. And so really, there should be circles of slightly different radius. But if I make a cut, and I know that the guy, these guys are at redshift 0.3, then for a thin shell around 0.3, it should look like this. A shell of 0.5, the circles will all be smaller, further away from us. And the shell at redshift 0.1, the circle should be bigger. Okay. However, what is the distance to redshift 0.1? Roughly, CZ is HD. And so CZ over H, that should give me D. And so CZ, so 3,000 times 0.1 is 300 megaparsecs. So from 0 to 0.1, that is roughly 300 megaparsecs. If I want to find a signal that size is 100 megaparsecs, there will be, what's the number, 27 or something of these independent circles inside this volume. That's not good statistics if the signal is small. And so we could not do this experiment until we saw bigger surveys. So until 15 years ago, it was not, although this effect was predicted in the 70s, we could not imagine seeing it. In fact, people wrote papers saying we will never see this effect as late as the 90s. Okay? But now surveys are big enough that people are beginning to detect it. And so, so why are people excited? People are excited because it's a physical scale, 100 megaparsecs. Okay? We know what sets the scale, and it is the same scale that we see as a spot in the CMB, the typical size of the spots in the CMB. Okay? And so that means that just like we could measure the geometry of the universe by saying what was the angular size of the spots, we could say they look like they are 1 degree on the sky, so that says the universe is flat for the geometry. Now we can play the same game, except now we get the same scale, but now in the galaxies, and the galaxies can be at redshift 0.3, 0.5, 1, 2. So we can do the geometry test at many different redshifts, not just at redshift 1000. And that means now you can literally map out the expansion history of the universe by taking redshift surveys at different redshifts. So it's beautiful, because the physics is simple. If you trust the CMB, this is the same physics, right? And so that's the idea. Okay, so here's the signal. So this is, you sit on a galaxy, and you count how many other galaxies are within 50 megaparsecs, within 70, within 80, and so on. And then, you know, if the galaxies were completely randomly distributed, you expect there to be some number. How many do you expect? If they're randomly distributed, there should be a number density of galaxies times a volume, and that volume should be 4 pi r squared dr. And so that means you sit on a galaxy, you count how many are in the shell of radius r, you subtract 4 pi r squared dr, you subtract that, and what remains is the extra, which should be the extra that you got because of this effect. But there's going to be extra anyway because gravity is making things cluster. And so this stuff here is because gravity made things cluster, the baryons were with the dark matter, all of that. But this one, that's from the baryons. Okay, that's from the baryon physics. Okay? So this one looks a little bit weird because they've plotted not this correlation, the excess, but they've plotted r squared times this, which means at 100 megaparsecs, they've plotted 100 squared times the signal. Okay, so the signal looks big, but you should divide it by 10 to the 4. That's why you need a huge galaxy survey to see it. Okay, so in reality, this thing is a tiny little bit. Okay, but it's there. Okay, with high statistical significance. Okay, it has the peak that we want. And now let's think a little bit about this. Let's make the connection to the CMB. So in the CMB, we'll do the CMB in a second. First to the power spectrum. So in the power spectrum that we just talked about, we said there's the CDM shape The CDM shape is, it rises as k and it drops as k to the minus 3, k over k4, okay? Plus the piece that came from the baryons, which we said should be some slight oscillation. Let's try to get a feel for that oscillation, okay? In real space, this is a spike, no? It's a shell of 100 megaparsecs. The shell of 100 megaparsecs means you can either say it's a delta function at 100 megaparsecs, and I want to take the Fourier transform of the delta function. If the delta function is at 0, then the Fourier transform is a constant. But if the delta function is not at 0, then it's an e to the I, right? And that guy looks like the J0. So that's why I wrote the J0. It's the Fourier transform of this guy. If you don't like imaginary numbers, you can think like this. You can think, if you have a shell is the difference of two spheres. A sphere is, a sphere is basically a J1 Bessel function. If I take the difference of two of those, you get the J0. Okay, so either way, you'll get your J0. Then you say, oh, the spike was not a spike. There was some thickness to the last scattering surface. The baryons were not perfectly coupled with the photons, so this delta function was not a perfect delta function. Because of that, the delta function was smeared out a little. As a consequence, these oscillations here, you can see them here, but once you are here, they have been damped out because it's not a delta function, it's a slightly smeared out delta function. Okay? And so it's easy to see the first couple of bumps, but not after that. In fact, you can see that a little clearer here, because what they did is they fit the expected, they fit a kind of smooth model to this, and then they divide by the smooth model so you can see the oscillations more clearly. Okay? But you can see the amplitude of the oscillations is decreasing. Okay? And that's the fact that this was not a perfect delta function. It's a delta function smoothed with a Gaussian. Okay? The signal in real space is this scale. The signal in Fourier space is, this is sine kr over kr, is the r, so it's the frequency of the oscillation. So it's this spacing. Okay? So you're measuring very different systematics. No? Here you're looking for a single scale. Here you need a bunch of these peaks in order to estimate the frequency of the oscillation.
This frequency is kr, basically.
This frequency is kr. Yeah, so that's a sine kr over kr. That's basically that plot there. Yeah.
The oscillations, in the context of this, how will you say what is the scale of homogeneity? Because usually you say scale of homogeneity is 100 megaparsec.
Yes, yes. So there's two ways to answer it. So one way is, so this data is still from a few years ago, but this thing actually goes through 0. Okay, so it actually goes. Okay, so I'm 50. Okay, when I did my PhD, then people never thought they would measure the baryon oscillations. So people didn't even put them in their models. They said, why should we put little wiggles on the power spectrum? They just put the smooth guy. If you put the smooth guy, that one goes through 0 here. Okay, it goes through 0 and then it remains negative and gradually comes up. So the scale of homogeneity was 70 megaparsecs, the expected scale of homogeneity. But this would drop. So remember, we're multiplying by large numbers, no? We're multiplying by 10 to the 4 on this scale. So this is actually a small thing. So when it drops below 0, it's just a little bit below 0. Now if to that thing that's a little bit below 0, you add a delta function, that brings you up above 0 for now quite a while, and you only cross 0 at 160 or something like that. So if your definition of the scale of homogeneity is the zero crossing, then it's of order 200 megaparsecs. But if your definition of the scale of homogeneity is that you measure this spike wherever you measure it in space, then we see this spike in nearby volumes and also in distant volumes, and so there's still, I guess, some debate on what to call the scale of homogeneity, but at some level the discussion is fine. It's not obvious that zero crossing is the best choice, but it's a hard thing to measure, no? Anyway, so this is giving you the correspondence between the real space signal and the Fourier space signal. Okay, and you see both quite clearly. So just to remind you, that's what the CMB looked like. We went through this argument. Here, I'm showing you the CMB on top, and I'm showing you except I'm showing you the CMB. It looks almost like that other one. The difference is that other one, remember, is projected on the sky so it's a spherical harmonics thing. And it actually came from some 3D thing. And we had that brief animation of how you go from 3D to 2D, right? To see the ones with the photon scattering, with the oscillating waves, to see how you get an angular pattern from the 3D pattern. So this is the 3D power spectrum that gives rise to this one in 2D, this one on the sky, okay? And because it's 3D, we can compare this 3D guy with the 3D one for the matter, right? Because they're supposed to be the same physics, right? So this is to show you where the things are, where the spikes are, okay? And in the radiation, so in the photons, the oscillations are very obvious. And that's because in the photons, you're seeing only the photons and the baryons. In the matter, you're seeing the dark matter with a little bit of baryons on top that are showing the oscillations. And so the oscillations are much less obvious here than they are in the CMB. But they're in the same place, okay? So that's, again, just to make the point that it's the same physics that's giving both signals. Okay? And so using it as a standard rod at different distances from us is a good thing to do. Yeah? Okay. Why are they anti-correlated? Good. So does everyone see that? So the peak here is a trough here. Yeah? And so this is because, so in the CMB, you're seeing, this is when the baryons and the photons are compressed, and then they are released, they are compressed. So the alternating peaks are alternative. You remember the compression and rarefaction of the peaks, okay? And so the maximum signal is at compression and rarefaction, compression again, okay? So here, what you're really seeing is you're just seeing the net effect of it's really the velocities, right, that was pushing the baryons. And the velocity and the density are anti-correlated with the photons, because with the photons, so you have an oscillation like this, no? So when you are zero velocity is the most rarefaction, then you come in, the compression, you have the biggest velocity, and so on. Yeah? So the densities and velocities are 90-degree out of phase. And the matter signal is sensitive to the velocity rather than to the density. And so that's why you're seeing them out of phase. And so it's actually another consistency check that everything has come out right, yeah, to get them out of phase. And so the last year or so, there have been papers in the literature asking, can we constrain physics, can we constrain models for the dark matter by having this be out of phase with this? Meaning they should be 90 degrees out of phase, but what if it's 93 degrees? Does this constrain particle physics? And there's some interest in doing that. Yeah. Okay. Of course, we'd like to do this at many different redshifts. Yeah. And so surveys were designed to do that. So it's a little late, so let's not worry about the fine print. You can get surveys with you only see the most massive galaxies, or you can get surveys where you try to see more galaxies. But so long as the spacing between them is 5 or 10 megaparsecs and not 100 megaparsecs, you will have plenty of 100 megaparsec pairs, so you can make the measurement. So this is different surveys. This was at redshift 0.3. This was at redshift 0.5. This is basically at the redshift 0.5, 0.6, 0.7. As the data came in and they had more pairs, then they could start measuring with better precision the signal. Yeah? And so this is just to show you, they're measured with high significance now. Okay? So that's in the galaxies. But any baryons should do this. And so one of the things we talked about was cosmology with the Lyman alpha forest, with the gas. So the light from the quasar shines through the gas on its way to Earth. And as it shines, if there's any hydrogen gas along the way, then the photon, if it's a very energetic photon, as it is traveling, it's going to get redshifted by the expansion. So as it gets redshifted, it will be just the right energy to excite hydrogen at this distance, or at this distance, or at this distance, and so on, and the hydrogen will absorb it. And so this is a map of the hydrogen. If it's a map of the hydrogen, there's more hydrogen, there's less hydrogen. So I can sit on the hydrogen, and I can count up how much hydrogen is close to me and far from me, because this is the distance. And so it's some number of megaparsecs. We can convert from this wavelength to megaparsecs. And so we can look for the same BAO signal in the baryons, where it's really just the hydrogen gas now, not the gas that made stars. The beauty of doing this is that the galaxy surveys are redshift 0.5, 0.6, because as they start going further away, they're faint, they're hard to see. These you can see at redshift 2, redshift 3. You can see the hydrogen gas because the quasars are at redshift 4. And so that's the measurement from the Lyman alpha forest.
This Lyman alpha is something which always confuses me. Lyman alpha forest, what is the accuracy with which we can measure the wavelengths?
It really depends on the telescope.
So what is the typical?
Okay, so with the Keck telescope, then it's of order tens of kilometers per second. So it's very accurate. With this one, with the Sloan spectrograph, it's much worse. But this is the other beauty of these surveys. And it's even maybe makes more sense to illustrate with this. Okay, so we're looking for a signal that is 100 megaparsec scales. And so I could make a grid here where the grid size was 20 megaparsecs. Okay, so I could smooth this and just show the 20 megaparsec smooth thing. And for that, I can look for a feature on 100 megaparsecs. And I'm allowed to do that. That's like saying, I didn't need to have a telescope that could see these as individual galaxies. All I care is that I know that there are some more galaxies here and there are a few galaxies here. Okay? And so I can have a lousy telescope and still do this experiment. And so this idea is called intensity mapping. And that is what the next generation of surveys that are measuring it with hydrogen, not the Lyman alpha forest, but with 21 centimeter hydrogen. There's one called CHIME, there's another one called BINGO. They're doing this. Okay, they're saying in radio you have lousy angular resolution. For this particular use, it doesn't matter. And in fact, for this particular use, you probably shouldn't try to resolve all the galaxies. Don't spend the money. You don't need to. Yeah? And so the Lyman alpha forest is the same idea, right? You don't need the lines to be perfectly well measured because you just want 100 megaparsec accuracy. And so you can live with, so CZ over H tells you kind of, the accuracy with which you have to measure. Yeah. SDSS and the other ones? For this one? Okay. So the SDSS survey was planned really to just do galaxy science. It was not at all obvious that they would measure this signal. In fact, it was one of their breakthrough cosmology measurements. So it was designed to measure, you can't quite see it, but there are a lot of little white galaxies here. That's the normal population. But in the collaboration, mainly there was a guy called Daniel Eisenstein who said, let's try to pick the brightest galaxies that we can then see to the biggest distances to do the BAO measurement. Because the Sloan survey really went to redshift 0.1. And I just argued that's not deep enough to see this. So he found a way to select from the galaxies, from the Sloan survey. For this, you need to know a little bit how surveys are done. So a survey is usually done in 2 steps. You have one step where you just take a picture of everything. And then you have a second step where you decide which ones to spend the money measuring the spectra. So different surveys make that decision differently. Sloan's decision was, we just measure the brightest. And we start from the brightest and we go down to some brightness and we stop there. And what we can get, we get. And so that meant that they have images for 100 million galaxies and they have spectra for only 1 million galaxies. So what Eisenstein said is that let's try to find the galaxies that from the image itself, we expect that they are at redshift 0.3. So we didn't have to spend the money on the spectrum. Having identified them, let's go measure specially spectra for them to do this experiment. And so those were called the luminous red galaxies that they then went out and they measured spectra for. But these were very unusual objects because they are super bright, so you could see them to redshift 0.3. And so they were very rare. And so the first BAO detection that came from this survey in 2005, it was significant, but it didn't blow everyone. I mean, it blew everyone away because it was so amazing, but statistical significance was not enormous. But its success said we should go back to the Sloan imaging, and now we should target other galaxies that we think are at redshift 0.6. And so nothing has changed in the imaging. It's the same images from 20 years ago. Just a different set of objects spectra has been measured. And that was called the BOSS survey. The Baryon Oscillation Sloan Spectrograph, something like that. And the next generation of this is called the DESI. And that's, again, just going deeper, targeting galaxies at redshift 2. And so there's a bunch of groups doing it, all with different techniques for deciding which galaxies to target. Because measuring spectra is expensive. Okay. So now I'm done. Yeah. So we're done with the BAO. We've seen it in the Lyman alpha forest, so that's it. So planned surveys will see this to 1%. And so I'm done. Okay.